Hi guys, here's a little drawing of two lines cut by a transversal that I made. And I have one of the angle measures already on there, 134 degrees, 134.2 degrees. And I just wanted to talk to you about these angles up here as they relate to the other intersection down here. Now we've got, let's say, corresponding angles, we've got alternate exterior angles. But unless these two lines are parallel to one another, right, we shouldn't expect that we'd have any 134.2 degree angles down here. So that's kind of what we're talking about today. And I'm just going to measure this angle and show you that I'm getting something like 147 down here. So those aren't congruent. I would still call them corresponding angles because they're still both sort of in the upper part of those intersections, but they are not congruent. And I wouldn't expect them to be unless these lines were parallel. And so that's our lesson today, is actually working to get these lines parallel. And the way we're going to do that is by paying attention to the angles. So I'm going to try to get those two angles as close to congruent as I can. And if I can achieve that, I had it, did you see? Is this driving you nuts? Ugh. It's harder than it looks, guys. Ugh. You get the idea though, right? So if I can get those as close to congruent as I can, if I can get them exactly congruent, then those two lines would be parallel to one another. So that's the lesson for today. We actually have one new postulate and three new theorems, and they are really just the converse of the four that we learned the other day. And so let's just talk about these quick. We've got the corresponding angles converse. If two lines are cut by a transversal, two lines cut by a transversal, so that the corresponding angles are congruent. This theorem only works if you have corresponding angles congruent. So that would be like your given. If congruent, then we could say that those lines are parallel, which we wouldn't say normally because I don't see those little arrows on there or anything. But we can conclude that those lines are parallel if the angles are congruent. It's the same thing with all these theorems. If my alternate interior angles are congruent, if I see the swoop swoop, then I can say that those lines are parallel. If my alternate exterior angles are congruent, then I would know that my lines are parallel. And the last one, remember, it's a little bit different. If I knew that those same side interior angles were supplementary, if I knew that those measures added up to 180, then I could say that those lines were parallel. So today we have the same conclusion in each of our theorems. And so I just want to make sure, really make sure that you see the difference. So the ones that we learned about the other day, we had to know, remember, if the lines are parallel. We couldn't do anything unless the lines were parallel. If the lines are parallel, then we know that our alternate interior angles are congruent. So if parallel, then, and it doesn't matter which pair we use, so I'll just do alternate interior angles congruent. So the difference today is that it's really going to look like the same diagram, but the given information is different. Today your given information would be about the angles. So if you knew, if that's all you knew was the alternate interior angles were congruent, then what can we conclude? Then we could conclude that the lines are parallel to each other. The diagram winds up looking the same, but the thing we start with is different. So if our alternate interior angles were given to be congruent, then we can say that our lines are parallel. So really it is just the converse, right? We switch the if and the then. It's the converse of the theorems from the other day. How can you tell whether the sides of the flag of Nepal are parallel? That is actually the flag of Nepal. And we can see on a diagram there, they did some protractor work for us, right? So we can see that we have this little angle right here, marked congruent to that little angle right there. And those are, can you see what they would be? Two lines cut by a transversal, those would be alternate interior angles. So because the alternate interior angles are congruent, then you know the sides of the flag are parallel. And we would say that's because of the alternate interior angles converse. So you have to distinguish between which one you're using. Are you using the original theorem or the converse? So all the ones we're doing today are the converse. Can you prove that lines A and B down here are parallel? Explain why or why not. And the given information that they're telling us is that angle 1 and angle 2, their measures add up to 180, which is actually pretty convenient because what kind of angles are they? They're same side interior. And so we have a theorem like that, that if the same side interior angles are supplementary, then we know our lines are parallel. Which theorem is that? I'm going to call it the same side interior angles converse. So if our conclusion is that they're parallel, we're using the converse. Abbreviate it how you want. Same side interior angles converse is fine. Couple more examples. This one says to write a paragraph proof, and you know how I like words. So instead of writing a paragraph proof, I'm going to practice a little more of our flow proof that I showed you yesterday. So in the figure, here's what we know, and I'm going to mark everything that we know for sure. In the figure, A is parallel to B. So I'm going to put those little triangles on A and B. And I know that angle 1 is congruent to angle 3. That's what I know for sure. And what I'm going to try to prove is that X is also parallel to Y. And I'm not going to mark that because I don't know that for sure yet. I'm still going to check. In a flow proof, I'll start with my givens. And I'm hoping that at the end I can link up to a box that says X is parallel to Y. But that's not given. That's what I'm going to try to show is true. So what can I tell? If I have parallel lines, we learned this the other day, if I have parallel lines, here's my parallel lines, then I'm going to have some congruent angles. Well, I shouldn't even look at line Y right now. If I look at just line X and think of that as the transversal, can you see how angles 1 and 2 are corresponding angles? So I could actually say that as long as I know those are parallel, A and B are parallel, I can say that 1 is congruent to 2 because of the corresponding angles. And that's the original postulate. If parallel, then the angles are congruent. And then, okay, now I know something about the angles, and that's kind of where we're going with today's lesson. If we know something about the angles, then we can maybe show that we have some other parallel lines. Except for if I want to show that X and Y are parallel to one another, I need to pick some angles that are corresponding or alternate interior. So I think actually if I look at A being the transversal, if I can work on showing that 2 and 3 are samesies, then I could say that x is parallel to y. And I think I've got that. If I can bring these two bits of information together, do you see how those would link together? If 1 is congruent to 3 and 1 is congruent to 2, then I could say that 2 is congruent to 3. If 2 is congruent to 3, that was just a transitive property. If 2 is congruent to 3, what kinds of angles are those? If we're thinking of x and y, those are alternate exterior, and that's one of our new theorems today, is that if we know that our alternate exterior angles are congruent, then our lines are parallel by the alternate exterior angles converse. So what I'm hoping you can see is when to use the original postulates or theorems versus the converse. If parallel, then angles, versus if angles, then parallel. My last little theorem I wanted to show you, we don't use this a whole lot in proofs or anything, but it's a good one to have. If two lines are parallel to the same line, then they are blank to each other. So here's the example. If line P is parallel to line Q, and if line Q is parallel to line R, they're all parallel to each other, just kind of like a transitive property, right? So they are parallel to each other. And since it's a theorem, it could actually be proven. Personally, I think it's pretty obvious. I wouldn't need to see a proof, but it's a theorem. I could prove it. Each horizontal piece of the window blinds is called a slat. The slats in our blinds, each slat above is parallel to the slat below it. But it doesn't say anything about the very top and the very bottom. But if this one's parallel to that one and that one's parallel to that one, I don't think it's too much of a stretch to believe that the very top one would have to be parallel to the very bottom one.